Hi everybody. I'm going to introduce a lab where we're going to gather data for an object that is moving in a different way than our tractor or monster truck. So I'm going to show you the lab setup, and I'm going to show you what we're going to do for the software that's going to gather the data. So we're going to use a sophisticated device called a motion detector. Once I show you the setup and what the data is going to look like, then I'm going to switch to a mode where I'm going to show you on the screen how you get the data, what adjustments you have to make, and I'll kind of walk you through some of the analysis. So if you get stuck, maybe that will help you. The goal is to take the data, make a graph or two or three, and then build equations and make a prediction. So the last video I'll do will be where we're going to test our predictions. Once we do all that, then there will be the standard follow with notes to summarize the key points and then practice. So when you come into class next time, make sure you have questions on anything that you still don't understand. Okay, so here is our setup. So I've got a track that is at an angle, and I'm going to put a car on the track right here, a good old collision car. And this is simply going to roll down. And we're going to see how far it moves and the time it takes. To do that, we're going to use this neat little device called a motion detector. So what the motion detector does is it sends out sound signals, and those sound signals hit the back of the car, bounce off, and when they come back, it can say where it was, how much time it took, and then plot points on a software. So the software is going to be on a screen like this. So what I'll do is I'll release the car and get the data. It'll take data every 1/10 of a second, and then I will go to another video to show you how to interpret this, because we have to make some adjustments. All right, so we're going to look at the data sheet that goes along with the activity, and then I'm going to go to the actual data set that we collected when the car rolled down a ramp, and I'm going to show you how to translate the information from the data to this sheet, because it can be a little bit confusing. I'm going to start you, but I want you to be able to fill out the rest on your own. So let's make sure we're clear. We have a position, which you're going to put as L2 in your graph calculator, a time, L1. This blank one we're going to fill in later. And then you have average speed and instantaneous speed, which you're going to calculate later. So let's fill out these first two columns. So here is our actual data. So I want you to take a close look. At time 0, our position is at 0.28. And everything here just multiply by 100. In fact, I'm going to do that right now. So we're going to look at this middle column. I've just converted the left column to centimeters because that's what I want us to work in. So let me again point out. Our initial position at time 0 is at 28, so we're 28 centimeters away from the motion detector. To make our lives easier, I want to turn that into 0. Secondly, I want our clock to start once I've released the car. So if you look at these first few positions, they're all the same because I'm still holding on to it. So I'm going to call 0 when we start to see the car moving, meaning our position changes measurably. So it looks like right here, I'm going to highlight this cell, is going to be our starting point. Okay, for our time, and we're going to reference that for thereafter. So what I want you to go on your data table, where this says 28, okay, we're going to call that 0. So our initial position, and I know with Cami it's not going to be great for me, is 0. And I'm going to call this 0 as well. Okay, so 0, 0 is when the moment I release the car. It's 0 away from my starting point. That's going to be used as opposed to the distance of the motion detector and at time 0. So if I go back to the next, right here, we see that we're at position 29. So the distance I want is simply the 29 minus the 28, all right, which is 1. And then the time interval is from, right, if this is really 0, this is going to be equal, and you can do this on your own, this, right, minus 2.4. So my time interval, in other words, is 0.1. So I've gone 1 centimeter in a 1/10 of a second, so that's going to be what I'm going to put in here. My new position is 1, and the time here is 0.1. And I'm just going to repeat that process until I fill out the table here. If we wanted, you could skip by every 2/10 of a second, but I'm just going to keep it simple and go 0.1. So my next position is 32. So I'm going to take the 32 minus the 28, and I'm going to subtract to get 4. And the time interval is again is a next tenth of a second, so that's after 0.2. In fact, if I fill these all down, right, I get those time intervals right there. So again, it's 28 is my baseline, 32 minus 28 is 4. So my position after 0.2 is 4. So what I want you to do is to figure out what the rest are for the next 1, 2, 3, 4, 5, 6 time intervals. So we want to get, in fact, let me do you a favor, and I'm going to highlight all the time intervals in question, or at least a bunch of them. Let me just make them that rose color to help make them stand out. Okay, so everything you see here, you're going to subtract 28 from. You can do that later. What I suggest you do now, because I'm going to move on, is just write down these values and then do the subtraction later. So pause it here and get those, and then I'm going to pick it back up. Okay, so now what are we going to want to do with that? So we have the information. L2 is position, L1 is time. So if we scroll down, you're simply going to, in your graphic calculator, make a position time graph. If it's linear, you're going to make an equation right here in terms of d and t, and you're going to need to find a slope using your graphing calculator. If it's nonlinear, you're going to have to linearize it. So I just want to remind you what you have to do. So suppose it's a graph that looks like that. I'm not saying it's going to look like that, but we would recognize that as a square root, right? So we would say d, and this is really hard for me to draw, is proportional to square root of t. Okay, so using that, I would then go up to here and I would put square root of t as my column, and I would take all of these and square root them and fill in this column, so that when I go to graph in my graphing calculator, I would have square root of t here, and that should give me a straight line. And I can now make an equation from that line where I'd say d is equal to some number times the square root of t. Okay, so I will give you a bit of a spoiler. Your function is not going to be square root of t, so don't assume that, but that's how to process what I want you to do there. So now you have an equation that describes your position as a function of time. Okay, so that's goal number 1. I can't erase these. I don't know why it's not erasing. I'm just going to skip it. Now we want to make another graph. So if I look at the next bullet, it says calculate the average speed for each time interval. And that's fairly simple. What I would do is I'd take my position, divide it by the time. So in this case, the first one is going to be 0. Maybe I can write that in. The second case, I want to take the distance. We went 1, and the total time was 0.1. So 1 divided by 0.1 is 10. Whoops, that's an awful 0. The next one, it's 4 divided by 0.2, which I believe is 20. Okay, so you keep doing that all the way down. So these average speeds, boy, that does not look like a 10. So these average speeds you'll see are changing. Then what I ultimately want is the instantaneous speed. Not how fast it was going on average from the beginning to the point in question, but how fast it was going at that point in question. So at this point you don't know how to do that, so I'm going to tell you how to do it, and we'll learn why that is later. You simply take your average speed and you double it. So if I go back up to here, this is still clearly 0. And then after 1/10 of a second, we're going 20 centimeters per second. And then the next one, if I double this, it's 40, and so on and so forth. Okay, so you fill that out. And so once you have that filled out, you're going to go to here, and on your graphing calculator, you're going to enter a new graph. So L2 this time is your instantaneous speed. So you're going to plot that versus time. It should be linear. Okay, and when you do that, you're going to make another equation where it's going to, so you're going to find a slope, make sure you put proper units. You got to work that out. Okay, so label the units here, label the units here, do the algebra off to the side. Don't make a silly mistake because it's easy to do. Put the units, and then write the equation in terms of v and t. So don't give me an y or an x. So v is going to equal some number times t. I would expect a very small or 0 y-intercept, so if it's really tiny, you can ignore it. Then I want you to interpret that. In other words, interpret this graph in words. I've started off, as time increases, explain what goes on with speed. Very specifically, there's 2 key statements you should make about that. Then lastly, to see if these equations are valid, I want you to make a prediction. I want you to use the equations to predict where it's going to be and how fast it's going to be after 1.5 seconds. Okay? So once you do that, then I'm going to go back to our data and I'm going to say what it actually was. So pause it right here, do all that, and then once you've got that all done, restart the video and see what the predictions are. So let's look at your predictions. So you should have had essentially the equation x equals, or d, I'm sorry, equals some number times t squared. I don't know what the value of your slope came out to be, but it should be that. And then this one should be v equals a different number times t. In fact, if you did things right, this slope of this second graph should be close to twice the slope of this graph. Maybe not exactly, but hopefully it's fairly close. So let's look at what our prediction, where that corresponds to our data. So if I go back to our data table, I've highlighted in green what corresponds to 1.5 seconds. Now that's really 3.9 seconds, but that's 1.5 seconds after we called 0. And we see that we're at position 163. But remember, our original position was 28, so our actual position should be 163 minus 28, which is 135. So it's traveled 135. Now, in order to get the instantaneous speed, we have to do 2 things. We first got to take the 135, divide it by 1.5. Okay, so when I do that, that comes out to be 90. That's the average speed for the first 1.5 seconds. To get the instantaneous, you double that, and so the actual speed is close to 180 centimeters per second. So go back to here. Okay, maybe write down results. Again, the position was 135, the instantaneous speed was 180, and then calculate the percent differences between what you got and what the cart says. Hopefully they worked out well, our data was valid. Okay, so hopefully this makes sense. You'll have a tutorial follow-up to put this all together.